So it gives me great pleasure to introduce our final speaker, Samuel Stark. He's a final year PhD student here in Cambridge, supervised by a suspicious character with a grey beard and a red jumper. Samuel's been working on extending capabilities across the whole system on chip, and in particular, looking at alternative forms of capability and how those might be used to secure untrustworthy I/O devices. Over to you, Samuel.
Thank you, Simon. Hi, I'm Samuel. I've spent the last 4 years or so on my PhD here at the lab. And yeah, as Simon has said, I have been looking into, and I've been studying a capability system, but it is a spooky and scary kind of capability system in that it is a capability system that is not CHERI. And I mean, I know it's really terrifying. And I hear you cry from the bleachers, why? But CHERI is great. We've just spent 36 hours hearing about how CHERI is great, and CHERI is great. It works in so many places, right? It works on kind of embedded form factors, processors with only one address space, the sort of CHERIoT kind of model. It works in more advanced application class processors and larger OSs, things like CheriBSD, and when it works in CheriBSD, it works both in user space and in the kernel. It also works if you're making new peripherals, trusted peripherals. You know, if someone's designing a new GPU, they could put CHERI in there. It can work. We've tried it. It does work. But a fundamental thing about CHERI's threat model is that it relies on trusted hardware. Anything that manipulates a capability or stores a capability has to be trusted. Otherwise, it could break the model, forge new capabilities out of thin air. And as we've just seen, as Johnny has just gone over, right? Not all peripherals can actually be trusted. You might have, we've heard about supply chain attacks, especially yesterday. But you might also just have hardware that is buggy. You might have software that's buggy. We've all been there. So we need a way to handle untrusted hardware and untrusted peripherals. And so as we've seen, right, Johnny again has just shown us the cap checker. Here's a kind of very simplified version of it, right? A harness around untrusted peripherals where the peripheral is completely unaware of capabilities as a whole. The trusted system fills in this list with CHERI capabilities there, where here each capability is effectively like a ticket granting access to a contiguous region of memory. And when the peripheral comes in and wants to do an access, we check against one of the capabilities in the cap checker, and if that succeeds, it moves further in, and the peripheral can interact safely with the rest of the system. And this is kind of a great example of a dichotomy that has existed in capabilities going back from like the 60s, 70s when they first started out, about these sort of ticket-style systems, which CHERI is an example of. And CapChecker really converts that into a C-list system, a capability list system, aptly named. And so what are the actual kind of properties of these two kinds of system? Well, with tickets like CHERI, they can be used and stored directly. I can take a CHERI capability, copy it as many times as I want, put it anywhere I want, and when I go to access memory, I just have to be holding a real capability. Like in the same sense, if I go take a train, I can put the ticket anywhere on my person as long as I scan it at the gate. Whereas with the cap checker, we've got that indirection that we've heard about, especially as Ericsson have been talking about before, right? Someone shows up, the peripheral shows up and wants to do an access. We have to check in a big list, and that might be searching the list. It might be indexing into the list. If you're not careful there, we are careful, but if you're not careful, you can end up losing the principle of intentional use, which is something that is kind of a cornerstone that CHERI relies on. Another benefit of the ticket system is that you have, again, effectively unbounded-ish amounts of capabilities. You can have as many capabilities as fit in memory. Whereas in the C list, especially in things like the cap checker, you do have a fixed size. The system designer provisions you with 128 capabilities. That is as many regions as you can share. But then on the flip side, tickets aren't all roses. With tickets, when you want to delete them, you have to, because they could be anywhere in memory. If you want to delete a specific ticket, you have to scan through all of memory sort of, by searching for copies. And again, this is something that we've heard about from Ericsson. Whereas in the C list, it's a lot simpler, right? You just go into the list and you delete an element. It's that easy. But then in the cases we already discussed, right, the other downside of the CHERI system is that we rely on this trusted hardware, whereas the C list provides this nice kind of asymmetry where trusted hardware fills in the list and untrusted hardware uses it. And so ideally, right, we want a system that has the benefits of both of these. And it could be a capability system. We've also heard about like the IOPMP and the IOMMU. These are older units that are kind of now industry standard that are designed for this sort of problem. But those, I would argue, even though they aren't using the capability language, they are forms of C-list. And they have the same sort of problems, especially the IOMMU. Performance is a real concern because every time you do a page table walk, and you have to do a lot of page table walks, you are searching through a list, and that takes a lot of time. So if we want a system with kind of both of these qualities, well, what can we do about it? Well, again, CHERI is not the only capability system out there. There's a huge legacy and a lot of ways that these techniques have been employed in the past. There are different approaches. They aren't all ticket systems. They don't all use tags. They aren't all protecting the same things. Sometimes they protect memory, but sometimes they protect access to more abstract things, like files or sockets or just objects. And then those systems operate differently. They have different structures, different approaches, different pros and cons that are applicable to different situations. And so if we are in this sort of new situation where we need to deal with untrusted hardware, we can look at all of these past systems and just make new ones. No one's going to stop us. So let's try that. We can start by looking at, again, some prior art, right? Google's macaroons, this was from about 2014, were a form of capability designed for the web. This is a kind of very threat-rich and target-rich space where you have trusted servers and untrusted clients, and they have to talk to each other a lot. And so these macaroons are tickets like CHERI, but they can be stored in untrusted clients. They can be manipulated by untrusted clients. You can, just like CHERI, you can take a macaroon, cut it down, gives 50%, like to give half as much access as it normally does, and then delegate that, share it with somebody else. These are the primitives that are sort of the cornerstones of things like compartmentalization. And the reason this works is because they use cryptographic authentication instead of a tag bit that has to be trusted. Every time the server issues a ticket, it comes with an authentication code which has been generated specifically for that ticket. Every time someone tries to use the ticket, you bring it back with the authentication code, and the server double checks. We know what we think that the code should be, and if the code is correct, the capability is valid. So then, if we've got this system, this seems like a pretty good primitive. It's a ticket that survives untrusted actors. But then how does revocation work? Well, authentication requires a key. As we just said, to generate this authentication code, you need a cryptographic key. You're going to have a lot of keys because you have a lot of peripherals that are doing a lot of different things. And so you can link each ticket to a key. The ticket will have written inside it which key it used. But it means that we can use effectively a list of keys. And you'll notice that this diagram now looks a lot like cap checker, right? Except that the peripheral is holding the tickets now. Whenever the peripheral wants to use a ticket, it does so with intentionality. It brings that ticket over. We load the key in from the key list, and we use that to verify. And this means we get the nice deletion properties of the other C lists. So if we want to delete, effectively invalidate a ticket, we just delete the key that it is associated with. And as a bonus, later on, we can reuse the slot that that key was in because we refill it with random data as a key. So even if it's harder to exhaust the list. And then the other nice thing about this system is we can still get our unbounded amount of tickets because you can have a many-to-one ticket-to-key relationship. So you can have way more tickets than you have keys as long as you're comfortable with revoking them in groups. And if you expose these properties to drivers, they can make intelligent decisions about which things should be grouped together. So yeah, this seems like it requires some adaptation. One thing about the original macaron system was that it was designed for the web. It's based on text. So we need to do some grunt work. We need to make a new binary format for these capabilities that is directly applicable to just sharing memory as opposed to sharing arbitrary objects. But those are things we can do, right? This is things that I've done. And so if we look again at our two kinds of system, we can see that really, the transition works. We do get sort of the best of both worlds for this kind of threat model, for this untrusted hardware threat model. And so great, it works on paper. Does it work in practice? Well, thankfully for me, yes. So we have designed hardware elements that actually do the verification, the cryptographic verification. We have taken peripherals and adapted them to use this new form of capability. We have taken operating systems, so we've implemented this on CHERI-SIMT and CHERI-BSD, new drivers to interact with the system and use it to expose memory, and indeed to interact with, to be very careful about we're not going to even touch memory that is still exposed to the device. And then the other cool thing about this is we've done micro benchmarks on our specific module that does the checking. And we find that we can reach kind of maximum DMA throughput with low latency in the sort of 10 cycle range. And this is super important because, again, the IOMMU, those sort of solutions are really not very performant, especially in the pathological cases that IO hits so often, which can be both. It's both just sad that it's not as performant, but also that it's actually a reason for people to turn the IOMMU off, right? You see it a lot where people accidentally turn on to like, oh, there's this extra security, get rid of it. And so this isn't just solving like a toy problem. It has like a real impact there. And so I understand that this talk has been maybe a little more abstract than something which was ostensibly technical. And I can, you can interrogate me about the technical stuff all you want in the questions. But the real takeaway I want everyone here to have is that CHERI is great, both because we have these fantastic implementations, but also it's just based on really rock solid principles. And these principles can be extended to work in more places that CHERI's basic threat model can't reach. And I would say that especially, it's not that we get rid of CHERI, right? Again, like CapChecker, right? We are layering on top of CHERI inside the CPU, but just applying this new model where it's more suitable. And so I would say that, if we want full system protection, we need these new systems, and the people in this room and the people online and the people who left early are, I think, uniquely qualified as people who already understand CHERI and its principles to start building these new systems so that we can really protect everything. And with that, I'd like to thank all of my collaborators in the lab, and especially Simon and Theo, and to thank you all for listening, and to ask if you have any questions.
Thank you very much, Samuel. Are there any questions? Oh, excellent. I'll sit down.
Thanks for a great talk. So in this design, can you a little bit talk about the impact on the bus architecture? Do you need some kind of support, or is it sort of
Yes. So one of the things about this capability format, especially, is that you do need to hold enough data, especially like in the authentication code, to be cryptographically secure and to use that authentication code. This is how we implement revocation, but it needs to be quite long. So the way we've adapted the bus architecture is we're assuming that we're going to be using this for bulk DMA. And we're looking at, especially we looked at AXI, which has separate address and data channels, both for read and for write. And so what we've done is we time multiplex the address channel. So because we assume that there will be multiple flits of data. So if you have 4 flits of data, we end up sending 1 normal address flit and then 3 flits to carry the capability itself. And then you need to make sure that you order those in the right way so that you can start verifying the capability as early as possible to get low latency. But yeah, especially for like the sort of 64-bit bus that you might have, you need 3 extra flits to pack that in.
Cool. Thank you very much.
Thanks.
Cool.
Oh, wait, I want to catch it.
Oh, thanks for doing that.
Any others?
Stunned silence. well done, Samuel. Oh, Ben.
Oh.
Go.
So what is the actual, I mean, you can't start, you can optimize the order for evaluation, but you can't start until you've finished evaluating, presumably.
So you might be stuck until you finish validating it. There are ways around. So some prior art that has looked at kind of similar approaches has, for reads, you might be able to start the read, and then if it turns out that the capability isn't valid, you could cancel it and just not send the data out. With writes, yes, you would be blocked. But at that point, you just need to make sure that you are, with an optimized AAS implementation, it's not that much higher, especially compared to other protection mechanisms like the IOMMU. Your P99 is much, much better.
Right, but there's an overhead, a latency overhead compared
Yes.
to
Yeah.
unprotected DMA,
Yeah. Oh, absolutely.
which is what you'll be measured against.
Yeah.
So, yeah.
Cool.
Oh.
Thank you very much.
Oh, hold on.
Oh,
Oh.
another one. Do you want to pass it over?
Wait, because I always wanted to throw this. Hey.
Wow.
Yeah, thanks for the talk.
Yeah, speak a little closer to the cube.
Yeah,
Thank you.
where do you actually check the capabilities here? Is it on the bus architecture or is it in another level?
Sorry, could you repeat that?
Where do you plan to check the capabilities of any access?
Oh, yeah. So in a similar sense to where the cap checker would be, you just have a unit between the peripheral and the main interconnect that takes in the capability metadata that's been attached, strips it off, compares it against the key, and does that check before passing it on to the rest of the main interconnect. Very similar to how the IOMMU, where the IOMMU would be, or where the cap checker would be, as we've seen.
But if we have several peripherals, it's every of them that we will have the capability checker with each peripheral we have, right?
So you could have a capability checker on each peripheral, or in cases where, I mean, in SoC design, you'll end up, if you have PCIe, for example, you'll end up with one protection unit at the PCIe hub, where you could have one unit that handles many at the same time. So, but yeah, and just like the IOMMU and the SMMU, you can put down multiple if you want to, if you want that better performance or compartmentalization or whatever.
Thank you.
Okay. You take the cube back.
Oh, yeah. Wait.
Cool. Thank you very much. Wonderful.
Thank you.